Hi everyone, this is going to be the first lesson on the subject of atomic structure and the periodic table for GCSE chemistry students. This is usually the introductory topic for the GCSE chemistry course. It's the first thing that generally you study when you start your GCSE chemistry course, and there's a very important reason for that. The science of chemistry deals with the observable, measurable properties of materials, their characteristics, their physical properties, their chemical properties. But in order to explain why materials have those physical and chemical properties, we need to make use of ideas concerning essentially invisible entities like the atom, the electron, and so on. And so in order to understand the properties of materials, we first have to make reference to the structures of these atoms and electrons and the way that they behave and interact with each other. And so this is perhaps the most fundamental topic of chemistry, and it shares quite a few ideas with the first lessons of the topic of atomic structure that you would study in GCSE physics as well. So those of you doing separate sciences for GCSE, you'll notice that we're going to be going over some of the same ideas that you encountered in the topic of atomic structure in the physics course as well. So, as always, let's start by taking a look at the learning outcomes for this lesson. So let's go over here to the GCSE chemistry course. So by the end of this teaching video, and also once you've completed the exercises, the quizzes, and the simulations and various other learning activities in the lesson page for this lesson on the GCSE chemistry course on the website, you should be able to do these various things. Now, the key thing that we're going to be focusing on in this lesson is not just atomic structure, but also how the different models of the atom have changed over time. Now, the idea of scientific models is very, very important. It fits into a theme which runs through all of your GCSE science courses, and that's the idea that our models of the way things work will change over time, depending on the available evidence, and when evidence appears to invalidate earlier models, new models are developed to encompass that evidence. So we're going to be looking at the ways in which the atomic model have changed over time, to include the models proposed by various scientists. And we're also going to be looking at the definition of what we mean by the term atom and the various key terms which are related to the term atom in chemistry and also in physics, things like mass number, relative atomic mass, atomic charge units, and so on. So we're going to be looking at these concepts, and as always, if you have any questions by the end of this lesson, if you're enrolled on this course on my website, you can simply go to the lesson page where you'll be able to ask questions in the live chat, or you'll be able to send me private questions via the private messaging function there as well, and I'd encourage you to do that. Okay, so let's start with the concept of the atom then. So by now, from your teaching in earlier years of your science education, you should be familiar with the idea that atoms are incredibly small. Now, the idea of the atom is fundamental to the study of materials, of matter itself, because all matter throughout the universe, all matter throughout the universe is made up of these tiny particles called atoms. Now, you need to have a general sense of the size of atoms. Now, atoms obviously will vary in size, depending on which element you're talking about. But atoms are minute particles, and to give you an idea, a speck of dust contains many billions of atoms. And if we're looking at individual atoms, they're way too small to be seen under an optical microscope. So we need to be able to detect atoms through various physical experiments, and that's what we're going to be looking at, how these various models of the atom evolved over time as a result of evidence acquired through various experiments in physics. So the mass of an atom is an incredibly small quantity, and the standard units of mass in physics, of course, are kilograms. Now, the kilogram is a useful unit of mass to be using if you're measuring everyday objects, but when you're measuring something on the order of an atom, it becomes less useful. So the mass of an atom is incredibly small. 1 gram of hydrogen atoms will contain more than 600,000 million atoms, and this gives you a sense of just how small these things are. Now, over the last 200 years or so, various scientific experiments done by various scientists have led to the widely accepted model of the structure of the atom. Now, this is called the atomic theory. But the idea of atoms originated much earlier in ancient Greece in about the 5th century BC. And it started with this man. Now, arguably, there were earlier philosophers who talked about the ideas of atoms. So, for example, early Indian philosophers had a similar model to the atom. But when you encounter the history of the atom in Western science education, typically that history starts with this guy here, Democritus. So he was an ancient Greek philosopher, and he was the first person, at least in the West, to formulate an atomic theory of the universe, the idea that materials are not just continuous stuff, they're made of fundamental pieces of matter, which led to the idea of atoms. Now, he said that everything is composed of particles, which we now call atoms, from the Greek atomos, which means uncuttable or indivisible. And so, of course, the extension of that would be to say that these particles are physically indivisible. Now, we now know that this is not true, but at the time, he proposed as a philosopher that these particles, of which all materials are made, are physically indestructible, that they couldn't be divided into anything smaller or simpler. He also proposed that in between these atoms, there is just completely empty space, devoid of any material whatsoever. He also said that atoms are indestructible, that once they exist, that they cannot be destroyed. Excuse me, got a bit of a cold. So he also mentioned that atoms have always been and always will be in motion, and that there is an infinite number of atoms and also an infinite number of kinds of atoms which all differ from each other in shape and in size. So this was the kind of earliest Western formulation of the idea of atoms, and this was a philosophical formulation. It wasn't really supported by scientific investigation or scientific evidence as we would call it. It was simply arrived at as a result of philosophical argument between the atomists like Democritus, who believed that matter was composed of physically indivisible particles, and everybody else who considered matter to be essentially infinitely divisible. So where this came about was you essentially had two groups of philosophers, one of which thought that if you took a piece of matter and divided it down the middle, and then took one of those halves and divided that further into a quarter of the original size, and then kept dividing, one group of philosophers proposed that you could continue dividing that piece of material forever, getting progressively smaller and smaller and smaller pieces of matter. And you could continue doing this forever, and that you would get essentially an infinitely small particle. But the other group of philosophers, again led by Democritus, said that no, you would eventually reach a piece of matter that was so small that it was indivisible and therefore the physical fundamental unit from which all matter was created. And they called these atomos. Tomos means to cut or to divide, and when you prefix a word with a in Greek, it means not that thing, or the opposite of that thing. So atomos would mean the indivisible one or the uncuttable one. Now, looking at this description that Democritus gave of atoms, we can already spot ways in which our modern theory of atoms is different from this. So we now know, for example, that atoms are made up of smaller particles, protons, neutrons, and electrons, as we'll be talking about shortly. And therefore, they are not physically indestructible, nor are they physically indivisible. We also know that there isn't an infinite number of atoms and of kinds of atoms differing in shape and size. Atoms are restricted to the atoms that we know of in the periodic table. So here is our periodic table, and each of these symbols represents a different kind of atom, or a material composed of a specific type of atom that we call an element. And so there is a limited number of these. It's not an infinite list of different kinds of atoms. So the next major leap forward in our understanding of atoms and in the model of atoms came with John Dalton. So in the early 1800s, he defined elements as being composed of only one type of atom. He essentially was a chemist who discovered that elements would chemically combine with each other in specific ratios, and from these observations he led to a number of these led him to a number of assertions about atoms. But essentially the definition of an element comes from Dalton's work, an element being a chemically pure substance composed of only one type of atom. Now, like Democritus, he thought of atoms as being these solid balls with no internal structure. But again, of course, we know that that's not the case. So we now define an element in chemistry as being a substance composed of atoms, each of which has the same number of protons. Now, again, John Dalton himself didn't really know anything about protons, neutrons, and electrons. This is really more of a modern definition based upon his definition of elements as being composed of one kind of atom. So, this was John Dalton's contribution, the idea that the different elements were composed of different types of atoms, and yet he still thought that the individual atoms were simply these tiny solid spheres of material. So, on to J.J. Thomson now. So in the early 19th century, early to mid 20th century, Thomson showed that an atom contained small negatively charged particles, and so he showed by physical experiments that there was negative charge, that there were tiny negative charges which were contained somewhere within the atoms, and he called these particles electrons. Now, he also knew that atoms were electrically neutral overall, and so if there was negative charge, which he detected, and he called these negative particles electrons, if these negative particles existed within atoms and atoms had no overall charge, by extension, you could say that there must be some positive charge somewhere within the atoms. So he proposed a model of the structure of the atom which became known as the plum pudding model. He said that an atom must be made of a positively charged sphere, this diffuse positive charge in the shape of a sphere which contained these negatively charged particles that he called electrons. And so this became known as the plum pudding model, where you have a positively charged sphere within which you have these negatively charged electrons embedded like the plums in a plum pudding. So this was J.J. Thomson's model, but later on in the early 1900s, Ernest Rutherford's team of scientists, which included scientists named Geiger and Marsden, who themselves were very important for other reasons, they carried out experiments in which particles, alpha particles, were fired at a thin sheet of gold film. Now, according to the plum pudding model, if the plum pudding model was correct and these atoms were diffuse, positively charged spheres within which you had these negatively charged particles embedded, then in principle all of the alpha particles which were fired at this sheet of gold film should pass through that gold film. And so this is what he expected to happen on the basis of the plum pudding model. But he found something very different. When he fired those alpha particles at the gold film and he placed a photographic film behind that sheet, very thin sheet of gold, he found that many of the particles did pass through, but some of them were deflected at varying angles, and some of them were even reflected back from the gold film. Now, this shouldn't have happened if the plum pudding model was correct. And so he proposed, as a result of those observations, that an atom consists of a central nucleus where most of the mass of the atom is concentrated, and that this central nucleus is surrounded by the electrons. And he also predicted the existence of neutrons in the nucleus, although, as we'll see, the existence of neutrons was only shown experimentally by another scientist, James Chadwick, later on. So let's take a closer look at Rutherford's model, and we'll see just why he made these conclusions. So again, this is what Rutherford proposed. Rather than having a plum pudding model of the atom where you had a diffuse positive charge within which you had these negatively charged electrons embedded, that the atoms contained these small, dense nuclei where most of the mass, most of the actual physical matter of the atom was concentrated, and that the electrons were orbiting around that nucleus. And so what he was proposing was that most of the atom's volume was in fact empty space. And this would explain why many of the alpha particles fired at the gold film would pass straight through, and it would also explain why some of those alpha particles were reflected back because they would collide with the nuclei and be repelled backwards. And it would also explain why some of the alpha particles would be deflected through various angles. Now, To get a better idea of why he made these conclusions and a little bit more of a kind of, if you like, realistic representation of that model, let's take a look at one of these simulations from the PHET website. Now again, I sing the praises of these guys a lot, so I would thoroughly recommend that you guys go to the PHET website. You can just type in PHET simulations into Google and it will take you straight to the first result will be the PHET website, where you can find many of these very useful simulations for physics and chemistry and biology. So let's take a look at the plum pudding model. So in the plum pudding model, let's imagine that this is the gold film, the very thin sheet of gold that Rutherford was firing alpha particles at. Now alpha particles are simply helium nuclei. They are 2 protons and 2 neutrons all bonded together, and that's essentially what an alpha particle is. So looking at the plum pudding model, if we're firing alpha particles at a material like gold, and the gold atoms themselves were as the plum pudding model predicted, you would expect the alpha particles to pass straight through the gold film, and you would expect none of them to be reflected backwards or deflected through various angles. However, if we look at the Rutherford model, the Rutherfordian model of the atom is that you have small, dense nuclei containing most of the mass of the atom, and also the positive charges, as we'll see, the protons in an atom are all concentrated in the nucleus. Now again, if you're firing alpha particles at these, alpha particles themselves are positively charged. So the ones that come very close to the nuclei, as you'll see here, are deflected through various angles as a result of the electrostatic repulsion between the positive charges of the nucleus and the positive charge of the alpha particles. The ones that go relatively further away from the nuclei are deflected less, or they pass straight through. Some of them will be deflected straight back at various angles because they come straight at the nuclei. So again, to take a look at how this might work for a single gold nucleus, we see some of the alpha particles which are further away from the gold nucleus are deflected much less, whereas the ones which come very close are deflected through much sharper angles. So based upon these observations, Rutherford made the conclusion that most of the mass of the atom is concentrated at the center in the nucleus, and that the electrons orbit those nuclei in the volume of space around them. And so again, atoms are mostly empty space. So, the next person to make a significant contribution to the model of the atom was Niels Bohr in 1913. Now he, on the basis of Rutherford's theory, he proposed a model of atomic structure in which, again, the atom is small and dense and positively charged, but the electrons are orbiting the nucleus as waves. Now, when we get to things the size of an electron, you get into the weird and wonderful world of quantum theory. Now, electrons can be modelled as waves, standing waves, around the nucleus at various distances, or they can be modelled as particles which are moving around the nucleus at various distances along various surfaces. Both models are valid, and both models are useful, and again, the idea of a model is that it doesn't necessarily represent truth, it just represents our best understanding based upon available evidence. And so Niels Bohr was the person responsible for, among other things, the idea that the electrons are located at specific distances from the nucleus at which they orbit. Now, again, his idea of an electron was more as a wave, a standing wave at a specific distance from the nucleus. But again, we can equally model those electrons as particles as well. So, Rutherford predicted the existence of what he called proton-neutron pairs, or rather proton-electron pairs, because he didn't really coin the term neutron. But this wasn't really these particles, these neutral particles in the nucleus, weren't shown to exist until James Chadwick came along and did a series of experiments involving beryllium. So he took beryllium and he bombarded it with alpha particles, and he found that that beryllium gave off a very energetic stream of radiation. Now at first he thought this was gamma radiation, but further experiments showed that it was in fact made up of a stream of particles, each of which had the same mass as a proton, but no electrical charge. Now he was awarded the Nobel Prize for this work because this is essentially what led to the discovery of the neutron. So we see how these different models of the atom have evolved over time, going back all the way to the ancient Greeks, or perhaps even further if you choose to include the ancient Indian philosophers who had similar ideas, all the way up to the modern day. And with every new experiment, with every new set of experimental data that came in, the previous models had to be revised and refined to incorporate that new data. Until now, we consider an atom to be composed of a central nucleus where you find the protons and the neutrons, and this is surrounded by where the electrons orbit at these various energy levels. Now again, when you get to, perhaps those of you who get to study A-level chemistry or A-level physics, you'll find that the model of the atom is refined further. But for the moment, this is sufficient kind of detail as to the general basic structure of the atom. So we've mentioned protons, neutrons, and electrons quite a bit here, so let's talk a little bit about those. These are referred to as subatomic particles because they are smaller than atoms, and each element is made up of atoms which are unique in that they are composed of different numbers of protons, neutrons, and electrons. So, for example, this is a diagram, a very inaccurate diagram because it shows that the nucleus is much larger than it actually is. This is a diagram where we see the protons and the neutrons, which are coloured red and blue respectively, in the nucleus, surrounded by electrons which are orbiting the nucleus at these various different distances, which we call shells or energy levels. Now, this actually represents a lithium atom because every atom of every element is unique in the number of protons that it contains. Now, if we look at the periodic table again, we can see that this is in fact the case. So, we can see here that lithium has the atomic number 3. Now, many of the periodic tables that you're familiar with will show the atomic number in the bottom left-hand corner. This periodic table happens to show it in the top left-hand corner. You can always distinguish the atomic number from the relative atomic mass by the fact that the atomic number goes up by 1 as you go from left to right across a horizontal row or period of the periodic table. So here we see hydrogen has the atomic number 1 proton per atom. Helium has the atomic number 2. If we go to the next second short period, we have lithium at 3, beryllium at 4, boron at 5, carbon at 6, and so on. So lithium has an atomic number of 3. However, the mass number of most lithium atoms is 7, and the reason for this is that most lithium atoms contain 4 neutrons. Now, as we'll see, mass number is something different from relative atomic mass. The relative atomic mass of lithium, again from the periodic table we can see here, is 6.94. Now, this is a different thing from mass number. Mass number is simply the total number of mass units within an atom of a particular isotope, whereas the atomic number is the weighted average of the masses of the different isotopes of an element weighted according to percentage abundance. Again, we'll talk a little bit about the distinction between those two numbers shortly. So, it's important at this point to realize that when we're talking about atoms, we're talking about three-dimensional objects. Now, when you draw dot and cross diagrams of atoms in GCSE chemistry, you have to keep in mind that even though you're drawing an atom as though it's a two-dimensional object on a flat piece of paper, you have to keep in mind that it is in fact a three-dimensional object. The electrons are whizzing around in their respective energy levels in 3 dimensions. So try and keep that in mind when you draw diagrams of atoms or you're describing atoms. Now again, this animation shows electrons as though they are particles, but they can equally well be modeled as waves. They show some of the same properties as waves. They can show refraction, for example. They can show diffraction, and so on. So let's talk about the nucleus a little bit here. So the nucleus of an atom even in comparison to the tiny size of an atom, is in fact very, very small. It's a very tiny proportion of the total volume occupied by the electrons of an atom. Now, this is again a huge approximation and a huge generalization, but to give you a sense of just how small the nucleus is, even in comparison to the size of an atom, if an atom could be enlarged to the size of a football stadium, then the nucleus of the atom would be about the size of a golf ball. So that gives you a sense of just how much empty space there is in an atom. Now, electrons are incredibly small, even in comparison to the sizes of protons and neutrons. And the size of the mass of an electron is approximately 1,840th or so of the mass of a neutron or a proton. Now, typically this means that when we're considering electrons and we're comparing them to atoms, or we're considering them in the context of atomic structure, we don't consider them to have a significant mass at all. We say that they have negligible mass, that the mass can essentially be ignored for all intents and purposes. Now, again, there is a reason for this. And we'll talk about that in a short while when we look at these the properties of, or the characteristics of protons, neutrons, and electrons. Now, another thing to bear in mind is that nuclei, you don't really often talk about nuclei of atoms in a huge amount of depth at GCSE level. But if you want to properly understand the structure of atoms, you need to also bear in mind that nuclei are not static bodies. They don't just sit there and they're not just motionless within the atom. They are themselves in motion. They spin, the particles within them are also in motion. And so you don't need to really understand the motion. You don't really need to understand the geometry of the nucleus. That comes much later at A level and beyond. But you do need to keep in mind that within an atom itself, the nucleus itself is not static. It's not still. It's constantly in motion. And the particles within it, the protons and the neutrons themselves, are also in motion. So let's take a closer look at protons, neutrons, and electrons. Now, the protons and the electrons, they do have an electrical charge, and this affects the structure and the stability of atoms. So if we're looking at the various subatomic particles and we're comparing their relative charge and their relative mass, and again, these are not standard units of mass and charge, these are relative units, and I'll explain a little bit more about that in a second. So the protons have a relative charge of 1 positive atomic unit of charge, and a relative mass of 1 atomic unit of mass. Now, I stress that these are atomic units of charge and mass. These are not standard units. The standard units of charge are coulombs, and the standard units of mass are kilograms. But those units are not useful for measuring the charges and the masses of things like protons and electrons, for example. Instead, we use relative charge units and relative mass units, where we are comparing the magnitudes of the charges and the masses of these particles, comparing them with each other. So when we say that the proton has a relative charge of +1 and a relative mass of 1, and that a neutron has a relative charge of 0 and a relative mass of 1, what we're saying here is that the proton and the neutron have effectively the same mass as each other. They have a relative mass relative to each other of the same number of units, 1 atomic mass unit. Now, when we say that an electron has a relative charge of -1, what we're saying is it has the same amount of charge as a proton, 1 unit, but it's negative rather than positive. And again, we've said that the mass of an electron, even in terms of atomic mass units, is effectively 0. It's about 1,840th of the mass of a proton or a neutron. So the charges of a proton and an electron are opposite in sign, but they are equal in magnitude. And so within an atom, which has an equal number of protons and electrons, the overall charge of that atom is 0. It is electrically neutral. Now, before we go any further about subatomic particles and the structures of atoms, let's take a closer look at just why we use these relative atomic units of mass and charge rather than standard units of charge, which would be coulombs, and of mass, which would be kilograms. Now, the masses and the charges of things like protons, neutrons, and electrons have actually been determined to a very high degree of precision by experiments. So we actually do know what the mass of a proton is, for example, in in kilograms, and we also know similar things for neutrons and electrons. But we choose not to use standard units because the numbers that we arrive at when we're measuring in standard units are rather unwieldy and not particularly easy to use, and so we simplify things. So a proton, if we're looking at its mass in kilograms, the mass of a proton in kilograms is approximately 1.6726 to 4 decimal places. It has been measured much further than that, but we'll stick to that for now, times 10 to the power minus 27 of a kilogram. The mass of a neutron is approximately the same. It's about 1.6749 to 4 decimal places, times 10 to the power minus 27. Now the mass of an electron is way smaller than that. It's 9.1094 to 4 decimal places, times 10 to the power minus 31 of a kilogram. So we see here that the mass of an electron is several orders of magnitude smaller than the mass of a proton or a neutron. And so if we're talking about atoms, the mass of the contribution of electrons to the mass of an atom is effectively negligible. It can be considered to be effectively massless for the purposes of talking about the structure of atoms. Now, if we now look at their charges, charge is measured in a standard unit, coulombs. Now, the charge on a proton is, again, very, very small. It's 1.602 or 1.6022 to 4 decimal places, times 10 to the power minus 19 of a coulomb. Now, the charge on a proton is positive, so it's 1.6022 approximately to 4 decimal places times 10 to the power minus 19 coulombs of positive charge, and it's the same magnitude of charge on the electron, 1.6022 times 10 to the power minus 19 coulombs, but this is negative charge. Now, a neutron is electrically neutral. It has zero charge. So we see here that the proton and the electron have exactly the same size of charge, the same magnitude of charge in standard units of coulombs, but the proton, its positive charge, the electron, its negative charge. However, if we're looking at these numbers, we can already see that we're dealing in horrible numbers. If you're doing calculations with these, then obviously they're very unwieldy. They're not particularly nice to use in calculations. And so to simplify things, we say that, well, the proton and the neutron have approximately the same mass, and so we'll call this one standard unit of atomic mass, or 1 unit of atomic mass, and the electron, as we can see here, is negligible even in comparison to that in terms of its mass. So we'll call this effectively 0, or approximately 1,840th of the mass of a proton or a neutron. The amount of charge on a proton or an electron, this number here is called the elementary charge. Now, it turns out that, well, the term elementary charge means that it's the smallest unit of charge that can exist on an object. Strictly speaking, that's not true. Things like quarks, for example, have a smaller unit of charge on them. They can have 1/3 of this unit, but effectively, as far as ordinary average physics is concerned, and you don't get into the weird and wonderful realm of quarks and things like that, this is the elementary unit of charge. It's the smallest unit of charge that can exist on any physical object. And so this elementary charge is the same on the proton and on the electron in terms of its size. It's just opposite in sign. So, because these numbers, the mass of a proton in kilograms and the mass of a neutron in kilograms, are effectively the same, and because both the proton and the electron have the same magnitude of charge, the elementary charge, and these numbers are the same, rather than use these horrible unwieldy numbers, we can simply call this much mass in kilograms 1 atomic mass unit. And we can call this much charge in coulombs, whether it's positive or negative, 1 atomic charge unit. And therefore deal with much more simple numbers, which are much more usable and much more convenient to use. So that's the reason why we, instead of using the standard units of mass and charge, we choose to use these atomic mass and charge units instead. So atoms are defined as particles containing an equal number of protons and electrons, and so atoms have no electrical charge overall because the positive charges on the protons exactly cancel out the negative charges on the electrons. So if we look at our lithium atom again, we have 4 neutrons which have no charge at all. They are neutral, they have no electrical charge, they contribute nothing to the charge of the atom. We have 3 protons, each of which has 1 positive unit of atomic charge, and so we have a total of 4 positive units of charge, and we have 3 electrons, each of which contributes 3 negative atomic units of charge, and so if we add all of these together, we get 0 overall. And so this lithium atom, like all atoms, is electrically neutral. Now in chemistry, an atom, before it chemically bonds, is electrically neutral, but if an atom gains or loses electrons, it can become an ion. It's an atom which has gained or lost electrons and therefore no longer has the positive units of charge balanced by the negative units of charge. We're going to be looking at ions in the next topic when we look at ionic bonding, but for the moment just remember that an atom has no overall electrical charge. That's not to say that it doesn't have charge within it, positive charges and negative charges. It just simply means that the negative charges on the electrons exactly cancel out the positive charges on the protons and vice versa. But that's only if you're talking about an atom, not an ion. So electrons, as we've said, can be modelled as particles or as waves. So they show characteristics, they show behaviour which you would normally consider to be the behaviour of particles, but under other circumstances they can behave like waves. So in the modern theory of the atom, in the modern atomic theory, we can model them as either particles orbiting the nucleus of the atom at various distances, which we call energy levels, or we can model them as waves of energy, which are at specific distances around the nucleus, standing waves of energy. Now, we can say that both models are accurate, or both models are useful under different circumstances, but the exact nature of the electron is something that is undecided overall. Both models are useful under different circumstances. So we're going to be talking about the arrangements of electrons in more depth in the next lesson of this topic, but for the moment we need to talk about it in a little bit of depth, just to kind of introduce the ideas. So electrons, they can't just be found orbiting at random distances from the nucleus. They tend to stay at specific distances from the nucleus that we call energy levels. And when an atom has no electrons at all, any electrons that that atom gains will occupy the level of energy at the nearest distance to the nucleus, which we call the lowest level of energy, or the lowest shell, the lowest energy level. So some energy levels are near the nucleus and some are further away, and the structure of large atoms with many electrons, protons and neutrons becomes very complex. Now, the levels of energy that the electrons can occupy tend to occupy more electrons the further away you go from the nucleus, and so the lowest energy levels will occupy comparatively fewer electrons than the highest energy levels. Now at GCSE level, the idea of electrons and the structure, the electronic structure of an atom, the arrangements of electrons in shells or energy levels around the nucleus is somewhat basic. You tend to visualize it as these concentric spherical surfaces on which these electrons move. But later on, you'll actually find, those of you who go on to study chemistry at A level or beyond, in fact, those orbits of those electrons are considerably more complex in their shapes. Now, you only really need to know the structure, the electronic structure of the first 20 elements at GCSE. So everything from hydrogen to calcium, everything from atomic number 1 to atomic number 20. The electronic structure of elements beyond calcium gets considerably more complex, and you only really need to know those or be able to construct those at later levels of education, A level and beyond. So if we take a look at calcium, we'll find that calcium has a certain structure. The electrons are arranged in a particular way. So we see here that we have 2 electrons in the innermost energy level, the energy level closest to the nucleus, 8 electrons in the second energy level, the second one out from the nucleus, 8 in the third, and the final 2 electrons go in the fourth. Now we see here that the total number of electrons in a calcium atom, if we add all of these numbers together, is 20. And this, again, is reflected in the number of protons. The atomic number of calcium is 20, and so a calcium atom, because it's electrically neutral like all atoms, will have an equal number of electrons and protons. So if ever you need to determine the number of protons or electrons in an uncombined, unbonded atom of an element, you can simply look at the atomic number. The atomic number tells you the number of protons in an atom. It also tells you the number of electrons in an atom, provided that that atom hasn't undergone chemical bonding like ionic bonding, for example. So again, we're going to be talking about the structure of the arrangements of electrons in a bit more depth in the next lesson of this series, but if we look over here, we'll find, and again, don't feel you need to understand this stuff, that the arrangements of electrons are a little bit more complicated. You can see these shapes over here. These are the actual orbitals in which you find pairs of electrons. And as you can see here, they're considerably more complicated than just concentric shells of electrons in a kind of spherical shape. But again, that's more kind of A-level chemistry. So, if the electrons are considered to be particles, which are moving extremely rapidly around the nucleus at specific distances, then if they could be seen, which of course they can't, but if we could visualize them in some way, they might appear like this. So this is really just to get you to visualize in 3 dimensions at a GCSE level where the electrons can be found. You can find a couple of electrons in the innermost energy level closest to the nucleus, another 8 electrons in the energy level beyond that one. At GCSE level, it's sufficient to say that there are 8 electrons maximum in the third shell. Later on, you'll find that that's not the case, but at GCSE level, that's fine. And then any further electrons go in the fourth shell, or the fourth energy level. So this is a kind of GCSE understanding. The correct number is 18 for the third shell, but at GCSE, usually it's okay to stick to the idea that this shell can occupy 8. So this is a sodium atom. Sodium has an atomic number of 11, and so we see here that we have a total of 11 electrons in this atom. We have 2 in the innermost shell, 8 in the second shell, and the remaining 1 electron goes in the outermost shell, the third shell of the sodium atom. So, to describe an atom completely, we need to know the numbers of each of those 3 types of subatomic particles which are present in that atom, the number of protons, the number of neutrons, and the number of electrons. And we use these numbers to generate the atomic number and the mass number of that atom. So the atomic number is simply the number of protons in that specific atom of that specific element. Every atom of each element contains a unique number of protons because every element in the periodic table has its own unique atomic number. So hydrogen is 1, so all hydrogen atoms have 1 proton in them, and only hydrogen atoms have 1 proton. If we take lithium, on the other hand, only lithium atoms are atoms which contain 3 protons. So an element can be defined as a pure substance composed of atoms, each of which only have 1 specific unique number of protons. So lithium, the pure element, is composed of atoms which each contain 3 protons in them. And lithium, the pure element, is a soft metal. The other hand, chlorine is the only element which is only made of atoms which contain 17 protons. So the atomic number is unique to every element, and it tells us exactly how many protons there are in the atoms of that element. So the mass number, on the other hand, is the sum of the protons and the neutrons in an atom of a particular element, and the mass number can be different for different atoms of that element. Now, this is where some confusion for some students sets in, because the mass number is not the same as the relative atomic mass. If we look at the periodic table, we'll find that the number which isn't the atomic number, again, in the periodic tables that you're familiar with from GCSE periodic tables, typically the relative atomic mass will appear in the top left and the mass number will appear in the bottom left. Doesn't really matter. Some periodic tables like this one will portray them the other way around. You can always tell them apart though, because the atomic number is always a whole number and it always goes up by 1 as you go from left to right across a horizontal row or period of the periodic table. But the mass number, as you can see here, these are not the mass numbers because you can't have a fractional proton or a fractional neutron. These are the relative atomic masses of these elements. The mass numbers relate to specific isotopes of an element. Now, an isotope of an element is an atom of an element which contains a unique number of neutrons, which are different from one isotope to the next. So if we take a look at chlorine, for example, chlorine has 3 isotopes. There are 3 versions, if you like, of chlorine atoms. Now, only chlorine atoms have the atomic number 17. So all of these chlorine atoms have the atomic number 17 because only chlorine atoms have that number of protons. But as you can see here, this chlorine atom has a mass number of 35. And so this chlorine atom has 18 neutrons in it. This chlorine atom has a mass number of 36, and so it has 19 neutrons. This chlorine atom has a mass number of 37, and so it has 20 neutrons. The mass number only relates to an isotope of an element. An isotope, again, is an atom of that element which has a different number of neutrons to the other isotopes of that element. Now, what this means is that if you take all the chlorine atoms in the universe, they can either have 18 neutrons, 19 neutrons, or 20 neutrons, but they all have 17 protons because only chlorine atoms have that unique atomic number. So if that's the mass number, then why does the periodic table display this number, this fractional number, which sometimes confuses students because sometimes they think that this number is the mass number? This is a different number. This is the relative atomic mass. Now, the reason why the relative atomic masses sometimes have fractional numbers is because this is a number which expresses the average mass of a chlorine atom, for example. And this takes into account the fact that the different isotopes exist in different abundances. Now, what I mean by that is that if you take all of the atoms of chlorine in the universe, we've already established that there are 3 different isotopes, 3 different versions of chlorine atoms which have different numbers of neutrons to each other. But they don't exist in equal quantities. It's not like there are a third of all chlorine atoms are chlorine 35, the other 2/3 are chlorine 36 and chlorine 37. It's not an equal number of these. These exist in different relative abundances. So if we take a look at chlorine 35, we'll find that 75.78% of all chlorine atoms are chlorine 35. Chlorine 36 is very, very unstable and exists in such tiny quantities that its abundance is effectively 0% of all chlorine atoms. It does exist, but it's in incredibly tiny amounts, and so we can effectively consider it to exist as 0 abundance. Chlorine 37 makes up the remainder, approximately 24.22% of chlorine atoms. Now, the reason why the relative atomic mass of chlorine on the periodic table, perhaps the periodic table that most of you are familiar with from GCSE periodic tables, it's usually expressed as 35.5 or thereabouts. The reason for that is that this is the average of those isotopes, but it's weighted according to percentage abundance. And so let's look at why that's the case. Now, again, we'll talk about this another time in a different lesson, but let's take a look at why the relative atomic mass is 35.45. So if we take chlorine 35, which is the most abundant isotope of chlorine, we find that that exists as a relative abundance of 75.78. So the way that we calculate a weighted average is that we multiply the mass number of each isotope by its relative abundance as a fraction. So a relative abundance of 75.78% as a fraction would be 0.7578. So we do this, 35 times 0.7578, and then we add that to the relative, the mass number of chlorine-37 multiplied by its relative abundance, which is 24.22%, or as a fraction, 0.2422. So we do this, 37 times 0.2422, and we get the relative atomic mass of chlorine expressed as a weighted average. Now this is not quite the same as the relative atomic mass being displayed here, because I'm using these mass numbers rather than the actual atomic masses here. But you get the idea here. So the relative atomic mass, and again, we'll define this in more detail in a later lesson here. The relative atomic mass, which is the single number which is displayed on a periodic table typically, is the weighted average of the atomic masses of the isotopes of an element weighted according to the percentage abundance of those isotopes and compared to 1/12 of the mass of a carbon-12 atom. So again, we'll define that later. Now, the mass number, on the other hand, mass numbers only apply to specific isotopes of an element. So please don't get those mixed up. So the mass number of a particular atom of an element is simply the total mass in atomic mass units of that atom. And so if each proton has a atomic mass of 1 unit and each neutron has an atomic mass of 1 unit, then if we simply add the number of protons and neutrons in that atom of that isotope, we have the mass number, a number which expresses the total mass of that atom in atomic mass units. And again, we're not counting the electrons because the electrons contribute negligible mass. We can consider their mass to be effectively 0. So the way that the atoms are represented in the periodic table, we have the atomic symbol, and if we're talking about a particular element, we have the atomic number, which is usually expressed on the bottom left-hand corner, and again, if we're talking about a particular isotope of an element, we have the mass number expressed on the top left-hand corner, which is simply the sum of the protons and the neutrons found in the nucleus of that atom. So this shows that a lithium atom of this isotope has 3 protons and 4 neutrons, making a total of 7. So if ever you need to calculate the number of neutrons in an atom, you can simply subtract the atomic number from the mass number to find the number of neutrons in that isotope of that element. So we have the atomic number and the mass number, and this reflects the structure of the atom, because again, in an atom you have an equal number of protons and electrons, and so if the atom has an atomic number of 3, we would expect 3 protons and 3 electrons. The neutrons are simply the mass number minus the atomic number, and so we see we have 4 neutrons here. So 3 protons, 4 neutrons, and 3 electrons. And you can derive these numbers of subatomic particles from the mass number of a particular isotope and the atomic number. So if we take carbon atoms, for example, carbon-12, the isotope carbon-12, has a mass number of 12, it has an atomic number of 6, and so we have 6 neutrons, which is 12 minus 6, 6 protons, which is simply the atomic number, and 6 electrons, again, which is the atomic number. So all atoms of a particular element have the same number of protons and electrons. All lithium atoms have 3 protons and 3 electrons, and all carbon atoms have 6 protons and 6 electrons. So the atoms of each element have a unique number of protons and electrons. Now, the chemical properties of elements, the ways in which they chemically combine with each other and form bonds with each other, are determined by the arrangements and the numbers of electrons in those atoms. And in turn, we can therefore say that the structure of those atoms determine their chemical properties. So the factor which identifies which element a particular atom belongs to is the number of protons in the nucleus which again goes back to the idea of atomic number. So all lithium atoms have 3 protons, all carbon atoms have 6 protons, and all uranium atoms have 92 protons. Now, I'm going to skip past this exercise. Those of you who are in attendance here will have access to the lesson page, so you can try this exercise for yourselves on the interactive exercises, but I'm just going to skip past this for the moment. Let's just go ahead and go to the next slide here. Now, in later lessons of this topic, we're going to be talking about the arrangement of elements in the periodic table and how it reflects the various structures of those atoms and the numbers of subatomic particles in those atoms. But as we've seen already, if we examine the elements in these 2 rows that have been highlighted, we can see a pattern in their atomic number. The atomic number goes up by 1 as you go from left to right across the periodic table, as we can see here. Now, if you go down a period, go from one period to the next, we see that the pattern continues. We ended with neon at 10, and we continue the next period with sodium at 11, magnesium at 12, aluminium at 13, and so on and so forth. And so generally, as you go from left to right across the periodic table, we find that the elements increase their atomic number by 1 as you go from left to right each time. Now, because the number of electrons is equal to the number of protons, this has consequences also for the number of electrons in these atoms. And so as you go from left to right, the number of electrons in each of these atoms also goes up by 1. Again, I'm going to skip past this exercise. I'll let you guys have a go of that on your own. So we've already said that the mass of an atom is mainly in the nucleus, and that protons and neutrons have effectively an equal mass. We say that their relative mass is 1, and that electrons have a negligible mass because it's a tiny fraction even of the mass of a proton or a neutron. So the mass of an atom is found mainly in the nucleus, and it's equal to the sum of the mass of the protons plus the mass of the neutrons present in the nucleus. Now this, for a particular isotope, is called the mass number of that isotope, of that atom. Now, most carbon atoms have 6 protons and 6 neutrons, and so the mass number of most carbon atoms is 12. It is the most abundant isotope. But some atoms of carbon have different numbers of neutrons, and so atoms of the same element with different numbers of neutrons are referred to as isotopes of that element. So isotopes of the same element have their own unique mass number. So let's finish off now by taking a look at isotopes of carbon. So carbon 12 has a mass number of 12. It has 6 protons and 6 neutrons. And it has 6 electrons in an unbonded atom of carbon. And this would be the same in any other isotope of carbon. So there is another isotope of carbon which is less abundant, called carbon-14. So here we see carbon-14 represented as one of these diagrams. Now in this case, we have 8 neutrons and the same number of protons. We're dealing with the same element, and so it's got the same atomic number. We have the same number of electrons because, again, in an unbonded atom, which hasn't lost or gained electrons, we have the same number of protons as electrons. Now again, I'm going to skip past this activity here. Again, those of you in attendance can have a go at this for yourselves on the lesson page. So let's summarize what we've talked about here. Now again, most of these ideas are going to be revisited in later lessons of this topic, and I would encourage all of you to have a look at this, have a look at those lessons. And again, if there are any questions, please do ask those. I can see already those of you in attendance have asked a number of questions in the Q&A box. I'll get to those at the end of this lesson here. So let's quickly summarize what we've talked about. Atoms are tiny particles, and they're in constant motion. Atoms are composed of a central nucleus containing protons and neutrons, where most of the mass of the atom is concentrated, and the electrons orbit around this nucleus in concentric energy levels at different distances from the nucleus. The atomic number of an atom is the number of protons found in that atom, and it's unique to every element. The mass number of an atom of a particular isotope is simply equal to the number of protons plus the number of neutrons found in the nucleus of that atom. Atoms with the same number of protons but different numbers of neutrons are called isotopes, and atoms have the same number of protons as electrons, and this gives them an overall neutral electrical charge. Now, there is another rather interesting simulation on the PHET website, which you can have a go at yourselves. It's called Build an Atom, and there are 3 different simulations in here. You can start with this one, where you can actually add different numbers of neutrons and protons, and you can see which atom you're building. You can also see whether that atom has a net charge on it. So here we can see I've produced an isotope of hydrogen called deuterium, which has 1 proton. All atoms of hydrogen only have 1 proton, but deuterium is an isotope of hydrogen which has a single neutron. Now, at the moment, this is positively charged because all we have is this 1 proton. If we choose to add an electron, it goes in the innermost energy level, and we now have a neutral atom. However, if we continue to add neutrons, we now have tritium, which is still an isotope of hydrogen. If I add a proton here, we have a helium ion. It's a helium ion because it's not an atom, it's electrically charged. It has a single positive charge because we have 2 protons, 2 positive charges, and 1 electron. A helium atom is electrically neutral because it has 2 electrons. Now, the innermost energy level can occupy a maximum of 2 electrons, and so both of those electrons go in the first energy level, the one closest to the nucleus. Now, if I add a proton here, we go from helium to lithium. Lithium has an atomic number of 3. We have 3 protons, but this is a lithium ion because it has only 2 electrons, 2 negative charges to balance out the charges on 3 protons. So the overall charge, the net charge of this particle is 1 positive unit of atomic charge. If I now add an electron to this lithium atom, we see that it doesn't go in the innermost energy level, it goes in the next energy level, which can occupy a maximum of 8. Now again, this model of the atom that's being drawn here is inaccurate for a number of reasons. Firstly, because the nucleus is way smaller than it appears to be in this diagram in comparison to the electrons. The electrons are even smaller still, but it's also because these energy levels being shown in this 2-dimensional diagram are not an accurate representation of the way that these electron energy levels work. In fact, they exist as these clouds of electric charge. And again, later on, when you study chemistry at a higher level, perhaps at A level or beyond, you'll find that these clouds, these orbitals as they're called, each of which occupy a pair of electrons, can exist in these rather weird and wonderful shapes that we see in the periodic table here. So you can see here. Now, this is actually quite a useful simulation for you to play with because it gives you a sense of, it gives you more practice calculating the relative numbers of protons, neutrons, the net charge, and so on. You can even see whether or not these are stable or unstable. So this isotope of lithium is unstable, but if we add another neutron, it becomes a stable isotope. Now, stability and instability gets into the idea of nuclear radiation and radioactivity and decay and things like that. So before we finish this lesson, there's one aspect of atomic structure that we haven't really mentioned in enough depth to cover the learning objectives, and I'll just cover it here now. And this is the size and the scale of atoms. Now, I know we've talked about it in general terms. We've talked, for example, in specific terms also of the masses and the charges of the subatomic particles that make up atoms. But how small are atoms really? So I would direct you to this simulation here. If you type in the scale of the universe 2 into a search engine like Google, you'll find this web page. You do need to have Flash enabled on your browser to fully use it, but I would encourage you to take a look at it because it's actually very interesting. It shows the relative sizes of things on a diagram as they actually exist in terms of their relative sizes to each other. So here we can see the average human is about 1.7 meters tall. Now, to get to the scale of atoms, we have to go much smaller. So here we see the size of an ant, 4 millimeters, 4 times 10 to the power minus 3 meters. If we go down to the scale of infrared wavelengths, we're now down to millionths of a meter or micrometers. If we go down to, for example, organelles like the mitochondrion in cells or bacteria, we are still at the scale of micrometers, but if we now get down to things like the HIV virus, we're now measuring things in billionths of a meter, nanometers. If we go smaller still, we start to get to molecules like glucose, which are measured in picometers. And finally, if we get down to the scale of atoms here, we're now measuring in a unit of size called angstroms. Now, angstrom is a unit of measure which is typically used to measure things like the sizes of atoms and the lengths of chemical bonds. Now, at this scale, an angstrom is 1 × 10⁻⁻10 meters. So it's a very, very small unit of measure, which is used to measure the scales of atoms. And so here we can see the smallest atom, the hydrogen atom, and even smaller, we get down to the sizes of nuclei. So you see here just how small you have to go to get to the size of a nucleus. If these are some of the smallest atoms here, you have to go way smaller to get to even some of the largest nuclei, like the uranium nucleus. And now we're down to a scale of 10⁻⁻13, 10⁻⁻14 of a meter. If we want to look at the size of protons and neutrons, we're down to 10⁻⁻15 meters, or femtometers. If you want to get even smaller and even weirder, here's where you get to the domain of the quarks, attometers, or 10⁻⁻18 meters. And they have rather interesting names, like the down, or the strange, or the up, or the charm, or the bottom quarks. And you can go even further if you really want to, right the way down to the Planck length, which is the fundamental unit of length. But I'm digressing somewhat into higher level physics territory there. So I'd encourage you guys to use this simulation here because it gives you a sense of just the scale of these things. And if you really want to go, if you really want to get strange in the opposite direction, you can go to very large things, like for example, comparing the various astronomical bodies in the solar system, and then getting into things like clusters and nebulae and superclusters, and even things like the strange attractor, or the great attractor rather, and the scale of the observable universe, 10⁻26.8 meters. Anyway, guys, I'm going to go into the Q&A session now with the students in attendance, so I'm going to stop the video here. I hope that was useful to you, and I will see you in the next one. Take care.